Yeah. All right, let's get started. Today, we are talking about feedback. The homework was posted. Hopefully, you've at least downloaded it. It's a shorter homework set, so in theory, it should take you less time. All right, so today we're going to talk about feedback. Professor Broderson has started to talk about feedback already. I have some set material that I can go over, but do any of you have any questions about particular material with regards to feedback that you want me to make sure that I cover? Yes?
Can you talk more about how to tell a circuit is what kind of feedback?
Yeah, and so the question was, how do you tell what kind of feedback the circuit employs? And unfortunately, there are some rudimentary techniques, and I actually have that. That's sort of the beginning of what I wanted to talk about. In reality, it's a bit tricky, and it just takes insight and kind of pounding your head against the wall until it becomes obvious. Or at least that's what it worked for me. And when I was an undergrad, it takes a while to get the hang of. My personal opinion is that the Gray and Meyer book has a very rigorous mathematical treatment of it, but it's one that just gets too involved too quickly and you lose perspective. The Razavi book has a more simple mathematical treatment. I think the examples in the Gray and Meyer book are better, though, when they actually put down actual circuits. They're all bipolar, but who cares? I mean, an active device, by and large, is an active device, and the principles here are basically the same. So really looking through the examples in Gray and Meyer is a really good way to sort of understand how they determine what kind of feedback it is. You have a circuit, you think, oh, it's series shunt, and it turns out to be shunt series or series series. And even that terminology can be confusing, and I'm going to talk about that a little bit. So, any other questions about sort of basic topics within feedback? No? Okay. So the basic feedback circuit. Ugh, I don't much like this pen either. I will find one I like. So does this show up? No. All right. How about this one? There we go, feedback. So the basic feedback network looks like this. Let's call this X error. Okay, so this is the basic feedback network. And if all your circuits looked like this, your life would be much easier. It comprises of an input, obviously, and I called it X in rather than V in because for all you know, the input could be a current, it could be a voltage, it could be something else, and it could be a charge, could be whatever. And the output is X out. No guarantee that the input and the output are the same units. You can have circuits that have a voltage input and current output or vice versa. You've got a forward path gain, a gain circuit A that has a gain of A. And I drew this little arrow to indicate that the direction of the gain of this block is purely unidirectional. And this means that, you know, X out equals A times X error. Okay? It's a purely unidirectional ideal network. Similarly, let's call this XFB. You've got a feedback network where basically XFB is equal to F times X out. And again, the assumption is made that this is purely unidirectional. Okay? In reality, that never happens. And in general, in circuits, A is an active network, active circuit with high gain, or really in feedback theory, A is typically quite high. F is typically a passive network, not always. With so A is typically much greater than 1. F is typically less than or equal to 1, although not always. Okay? So from this network, you can do the math and solve the closed loop gain. Okay, so there are some various terminologies to this as well. There's the open loop gain. Okay? The open loop gain means what is the gain from X out to X in if you break the loop? X out over X in, loop broken. Okay? So if you break the loop, say here, you break the loop somewhere sensible. What's the gain? What's the open loop gain? It's just A. Okay? There's also the loop gain. The loop gain is basically traverse the loop. You can see that there's a feedback loop here, and calculate what the gain is around the loop. So you start at X error and go to X feedback. See, and that's basically the loop. So you can see that the loop gain is equal to AF, right? Okay, and it's sometimes, in Professor Broderson's notes and in a lot of books, the loop gain is called T. Okay? Yes?
Does that, everything's instantaneous when you're talking about a loop like that, right? So the output instantaneously is fed back to the input. There's no delays.
Well, okay, so let's not talk about delays in the discrete sense. Let's talk about delays. What does a delay manifest itself as? A delay manifests itself as a frequency-dependent gain, right? It could be a phase shift. So in reality, all these things are frequency-dependent. A is frequency-dependent. J omega is frequency-dependent.
I mean, when you go through this stuff right now, you assume that everything kind of propagates instantly, right?
Well, I could put J omega in here. I mean, this is pure. If I add the J omega, that is purely general. Like A of J omega, I can come up with an A of J omega that corresponds to a gain of 1,000 with a delay of 5 seconds, right?
Yeah.
And so it's purely encapsulated within the mathematical terminology.
So it's valid for either.
It's totally valid. Okay? Good question. So that's the definition of the loop gain. And this shows up a lot. You'll see that the term 1 plus T starts showing up just about everywhere. Okay? And obviously, and typically, in regions of interest, the loop gain is also much greater than 1. And finally, there's the closed loop gain, which is equal to, defined as X out over X in with the loop closed. And I suggested all of you do the math yourself to verify the answer that I'm about to write down, because again, this is something that's important, is it's equal to A over 1 plus AF. Okay? It's another very important result. And you can sort of see, well, hold on one second. The closed loop gain is the open loop gain divided by the loop gain, or 1 plus the loop gain. That term 1 plus T just showed up. Okay? And something else that's important to keep in mind so the open loop gain, or the closed loop gain, I'll even just put CL, closed loop gain, is equal to A over 1 plus AF. Okay. Given the constraint that AF much greater than 1, the closed loop gain roughly equals 1 over F. Okay? So therefore, you can get, therefore what this means is that the overall behavior of the circuit, and the primary reason we use feedback, is that if you look at this network, and we'll sort of get into why later, this active circuit with gain, A is much greater than 1, its gain isn't going to be very well determined. Over frequency, over process variation, over voltage supply. You probably saw some of that stuff in Project 2. That your gain kind of changes. You change an input common mode, the gain changes. But this feedback network can typically be set by a ratio of passive devices, like a ratio of resistors. Those ratios can be very well controlled. So it's you can sort of see that to first order, provided that AF is large, changes in A, which will invariably happen because of process variation and such, don't really change the overall gain of your circuit. So it's called gain desensitization or gain stabilization. If you need a very accurate gain circuit, like if I want you to make a circuit that has precisely a gain of 2, you probably are going to want to use feedback in order to accomplish that goal. Because, as we'll get to later, there are the feedback networks, the ratios of the feedback networks can be set much more accurately. Okay, so now, so that's the basics of feedback, and the question is, well, so what's all this series shunt, shunt series, and all that other stuff? Yeah?
Can you talk about what is the gain compared to closed loop gain?
Okay, it's all right here. Okay, loop gain is just the gain around the loop. Oops, let me bring it. It's gain around the loop. Okay? And you can see right away that it's AF. Okay? You traverse the loop, you sort of break the loop somewhere, and you traverse it. And here what I'm doing is I'm breaking the loop here, starting at X error, and getting to X feedback. And you can kind of see that, or you can kind of see that that's one traversal around the loop. So X feedback over X error equals A times F. Okay? Yep. And closed loop gain is the gain of this entire block, as shown. Okay?
So loop gain, you don't really take the extra circuit output and input, just the
Well, yeah, pretty much. I mean, it's a bit hard to say because a lot of times, like the way it's drawn here, the inputs and the outputs are very much decomposed from the rest of the circuit. That's not always the case. Okay? So this is, as I said before, if all your circuits looked like this, you'd have no problem doing anything you needed to do. Okay. So, as I said before, on this network here, X in can be either a voltage or a current, and X out can either be a voltage or a current. Okay? So there are 4 possible configurations. I mean, it's a 2x2, right? So the 4 configurations and actually, yeah. So X in can either be, so we'll draw the voltage, X out, voltage, voltage. And here's where the notation in the Gray and Meyer differs from the Razavi book. So if you've looked at the Gray and Meyer book and sort of the standard terminology, and this is what Professor Brodersen uses in his notes, is like shunt series, like talking about feedback networks in terms of shunt and series. Okay? And there's a direct correlation between whether or not the inputs are voltages or currents, but it's not necessarily clear why or how, and I wanted to explain how. So when we talk about, say, a shunt series network, for example, when we talk about a shunt series network, for example, the first terminology, the first term, is basically referring to what quantity you feed back. So it really is. It's this terminal. It's this term that you feed back. Is it voltage or current? And similarly, the second term of the shunt series is talking about what you're sensing. Okay, and so let's say we're sensing a voltage. So X out is a voltage. So in a little network, how do we sense a voltage? Voltage. So if we have some V out, and this is going to the output, we also need to sense this value. And how do we do it? We put some voltage measuring device this is our sense mechanism in shunt with the output voltage. We're shunting the output voltage. So if you sense an output voltage, sense output voltage, that corresponds to shunt, okay, at the output. So if you're sensing an output voltage, it's a blank shunt network. Yeah. It's either going to be series shunt or shunt shunt, okay? How do you sense a current? So let's assume we have some I out that goes to our output. We sense a current by putting a sensing device in series. So this is our sensing device. Okay? Everyone understand what I'm sort of showing here? Okay? So therefore, can I go back to this? If you're sensing an output, you're sensing a voltage at the output, it's called a shunt network. So at the output, shunt is synonymous with voltage, and series is synonymous with current. Okay? Now let's look about at the input. How do you feed back a voltage? So at input, how to feed back a voltage. So if you're applying here this is going to be your V error that's going to go to your amplifier. You've got your V in here, but you also want to apply some V feedback. And in order to do that, in order to apply some V feedback, you put your voltage source in series with your input source. See that? So therefore, feedback a voltage implies series connection. And so it's going to be a series blank network. Okay? Similarly, if your input is a current, and you want to feed in, I error over here into your amplifier, how do you do that? You put I feedback in parallel or in shunt with your input. Current. Okay? Everyone see that? Any questions? I'll leave this up here for a second. Okay. So going back to this, our four configurations. So I said if you feed back a voltage, it's series. Current is shunt. Voltage is series. Current is shunt. So either memorize this table or keep it handy, because it's much easier to figure out, okay, am I sensing a voltage or, well, sometimes it's easier to figure out if you're sensing a voltage or current, and sometimes it's easier to figure out if something's in series or in shunt. So you'll see that the relationship between voltage, current, and series shunt are inverted between input and output. So it gets tricky to keep track of, and I have to remind myself by going through this exercise every now and then exactly what kind of feedback it is. Okay? So, page 3 and 4. All right. So one last note, I'll put this here, is that ACL is equal to A over 1 plus AF, okay, which is equal to 1 over F times AF over 1 plus AF is equal to 1 over F times T over 1 plus T. Okay? So this is an exact expression. Before I said A closed loop approximately equals 1 over F, it doesn't quite equal 1 over F. You have some loss, T over 1 plus T is going to be less than 1, obviously. So you have some loss mechanism here due to non-infinite loop gain, but you can quantify exactly what that loss is. Okay? So, page 5. So let's talk about voltage feedback. Okay. This means you feed back a voltage at the input, which means it's series. This means you sense a voltage at the output, which means shunt. So a synonym for voltage feedback is series shunt feedback. Okay? And always the first term refers to what's fed back at the input, the second term refers to what's sensed at the output. So what will this look like in terms of general blocks? So we'll have some V input here. There will be some active circuit that creates a V output. Okay. We shunt off this output because it's shunt. Feed that into a feedback network. I'm drawing arrows to indicate the direction of the action. And this feedback voltage we subtract by putting in series with, so VFB, putting in series with this input. So you can sort of see how this is V error. V error equals VI minus VFB. Okay? Is that too small? That's too small, isn't it? Sorry, I keep doing that. And what we can also see is that V out is equal to A times V error, and VFB is equal to VFB is equal to F times V out. Okay? You can solve this, and as you expect, V out over VI is going to be equal to A over 1 plus AF. Something else that's interesting is that V error over VI is going to be equal to 1 over 1 plus AF. Okay? So what does that mean? That means that V error is going to be very, very small, right? Which means that the negative terminal of this amplifier is going to track the positive terminal. So as typically this node will be grounded. So as you increase VI, this node will go up. This node is going to track it, because 1 over 1 plus AF is much, much less than 1. Okay? So now something else that's worth considering is what happens to the terminal impedances for these networks. So in reality, this is going to be some gain block with some output resistance. So terminal impedances. Any questions? VI, this is this? VI is the input voltage. Does that help? Okay. So basically R in and R out. And there's a trick here. The trick is any series connection, if you've got series type connection, it increases the terminal impedance by 1 plus T times. Okay, and with a shunt, it decreases by basically 1 over 1 plus T. Okay, so what I mean by this is that you take the terminal impedance and divide by 1 plus T, and here you take the terminal impedance and multiply by 1 plus T. So that's a basic trick, and that's a shortcut that you can always employ. But let's sort of see how this happens, okay? So in the case of series shunt, which is voltage feedback, let's look at R out, okay? So our network looks like this. We've got our amplifier, which is A times VE, and it has some output resistance R out, okay? So normally, this amplifier has some gain, and it has an output resistance of R out. But now what we're going to do is connect this in feedback. So this is F. V in. Okay, so VFB, and just to keep things simple, I'm going to ground this node and ground that node. Okay. So if we were to just analyze the output, and we're assuming this feedback network is ideal. Okay, so that this has infinite input resistance looking in. It doesn't load the circuit. So if we were just to look at the output resistance of this amplifier block, we'd get R out. Okay. Now what we do is we inject a test current here, IX, and look at VX. Okay. And we assume that V in is tied to 0. So we're grounding out V in, ground out. Okay. So that, I mean, we do the basic technique to calculate what the R in is equal to VX, or actually this is R out. And I'll put a little dash there, R out prime, to indicate that it's a closed loop R out, is equal to Vx over Ix. Okay? So now we start doing math. Okay. So, well, let's look at the circuit first. We know that Ix has to flow through that resistor. There's nowhere else for it to flow. Okay? And we also know that VFB is going to be equal to F times Vx, right? Vx goes through this network, VFB, okay? And so therefore, V error is equal to minus VFB is equal to minus F times Vx. Okay? So just to simplify things, I'm just going to redraw this network again a little bigger. So V air equals minus F times Vx. So in here, this is A times V air. This voltage is minus AF times Vx. Okay. R out. Ix Vx. Just redrew the network. And so this is Ix. And so we know that Ix is equal to the voltage here minus the voltage here divided by R out. So it's Vx minus AF Vx over R out, which is equal to Vx times 1 plus AF over R out that equals Ix. So R out prime is equal to Vx over Ix is equal to R out over 1 plus AF. So what we've seen is that this is a series shunt. Okay? It's a shunt network at the output. Shunt networks reduce the terminal impedances by 1 over AF. And what do we get? We get R out over 1 plus AF. Did I say 1 over AF? I meant 1 plus AF. Shunt networks, just to repeat myself, reduce the terminal impedance by a factor of 1 plus the loop gain. That's exactly what happened here. Yes?
What happened to the feedback circuit?
Okay. So I did a simplification just to keep my drawing a little simpler, going from here to here. This feedback network I'm assuming is an ideal network. So basically VFB just equals F times Vx. So therefore V air, because this terminal here is 0, it's grounded out. So V air is just equal to minus VFB equals minus FVx. So that means A times V air is AF minus AF Vx. So I just replaced that voltage directly in there. So I just so that I wasn't drawing all day. What? What do you do in order to calculate the output resistance? You ground the input. Okay, and so you can do this with all sorts of networks. I gave you a real simple one, where it's clear that it's voltage feedback. But in reality, you're going to be given circuits that it's not so clear as to what kind of circuit it is, and hence what you're supposed to be doing. And that's where this stuff either gets tricky or fun, depending on your perspective. So, how many of you in your project use the supersource follower? Okay, a couple of people were asking me about it last week, so I thought I'd show you what it is, based on feedback analysis. So the supersource follower is a way to get really low output impedance. Like it's a source follower, but a source follower is an output impedance of like 1 over GM. What if you need an output impedance that's even lower than that? Well, you can use this technique. And this is just an indicative circuit, like to use as an example. So what we know that for a standard source follower, R out equals 1 over GM. So now what we'll do So this is what a supersource follower looks like. And we want to calculate what our out is. Okay? So now what we need to do is we need to identify, well, what kind of network is this? Are we feeding back voltage? Are we feeding back current? Are we sensing voltage? Are we sensing current? And this is where things are a little tricky. Okay? So can any of you sort of tell what we're doing in order to, whether or not we're sensing current or sensing voltage, and whether or not we're feeding back voltage or current? Anyone want to give a stab at it? All right. Yeah, I'll walk you through it. So basically, one way to try to figure it out is to redraw it in a form that fits into one of these networks. So then you'll see, when you redraw it, you'll see whether or not you're feeding back a shunt feedback amount, quantity, which means you're feeding back a current, and so on and so forth. So let's just start redrawing it. So this is VI, that's a grounded node. Okay. So this is, let's call this node Vx. And this node, now let's call this Vx and Vy. So this is Vx. And so this is VGS1. GM1, VGS1. R01. I'm just doing I'm ignoring GMBs and some of the other things. I'm just doing GM and R outs. Okay. So the second transistor, this is V out, GM2 VY, R02. Okay, everyone see this so far? And so what I'm actually doing, okay, so if we look here, so I've calculated Vy. It's based on VGS1, GMR out, and these current sources go away, and then gain that up to get V out. And what we can see here is that V out is equal to Vx, right? So we're taking V out. The negative terminal of V out goes to ground because these are all a common ground node, and we're doing this. Okay? And once I've done that, then it should start to become a little bit more obvious what kind of network we're dealing with, what kind of feedback we're dealing with. You can identify your main amplifier. I'm going to change color. Okay. And your feedback network here. Okay? So, can we see what this is? What are we doing at the output? Sensing a voltage. We're shunting off of V out to sense a voltage. What are we feeding back at the input? Another voltage. We're feeding back a voltage that we're putting in series with this. So this is a voltage, or series shunt, which is the exact same amplifier that we just went through, like when we were dealing with ideal blocks. Okay? So now, let's look at what's A? Oops, sorry, I can't move that off the screen yet. What is A equal to? the forward open loop gain? This is not tricky. Please, someone volunteer an answer. Gain from here to here, if you get rid of this loop, it's GM1, RO1, GM2, RO2. Right? No tricks there. So A equals GM1, RO1, GM2, RO2. Okay. What's the feedback factor here? 1. Good. Okay, great. So now let's calculate what the gain is, the closed loop gain. Just 1 second. Yes?
Why if like a A's in GM1 R1 is I thought one of them is a very source.
Okay. And this, okay, very good question. This is actually something I glossed over, is that when you break the loop to figure out what A is, like you've got this feedback network here, and you kind of need to figure out what to do with it. And so when you're breaking the loop and looking this way, it's into a shunt network. So when you're looking that way, because it's into a shunt network, you assume that it's a low impedance node. Okay? So therefore, actually, when you're calculating the main amplifier gain, you short this node to ground. Okay? Which is effective to, this is shorting V out, which is a short, which you basically break the loop. Let me bring this here. You break the loop here at Vx, okay? And this node you assume is grounded. Okay? So I'll redraw what the open loop circuit looks like. Oops, wrong way. Okay, it looks like that. And really what we're doing is that we have this current here, and we've got this dotted line connection to here. We know that that way is a shunt. So looking in this way, it looks like a short. And we know that dotted line that way is a series. So looking that way, we leave it open. So when we break the loop, this side becomes a short, this side becomes an open. And that trick, that step that you do, I think is the hardest part of feedback. Like, because it's like, well, because when you break the loop and figure out the resultant circuit, it is something that's a little different from what you had here. Because here you've got infinite source degeneration on this guy. So you're like, it's got no gain. But in reality, when you break the loop, you ignore that portion of it in this case. And so it just makes things tricky. But that's the way the math works out. Okay? So getting back to the mathematical analysis, we have a closed loop is equal to A over 1 plus AF, which is basically a big quantity over 1 plus a big quantity equals 1. Right? Which is basically equal to 1 over F, as we expected. Okay? Now let's figure out what R out is. So we could go through the tedious step of injecting a test current and solving the small signal equation, but we've already done a lot of work here. And we know that this is a series shunt network. So R out prime is going to be equal to R out of the open loop divided by 1 plus T. What is R out of the open loop amplifier? No, just the output impedance. It's just RO2. Okay? So it equals to R out 2 over 1 plus GM1 RO1 GM2 RO2. So let's ignore the 1. So R out prime is equal to 1 over GM1 RO1 GM2. So look at that. This is a lower impedance. This is much, much less than 1 over GM1, which is what you get for the standard source follower, hence its name. Okay? Any questions on that? All right. So I've shown you what did I show you? Series shunt networks. And just keep in mind that there are lots of other topologies that could be apparent, that could come up. And do I have time to go through this? Is this the same thing? Give me 1 second. All right, let's just look at one other topology so that we can, we're not going to calculate everything, but let's try to figure out what kind of network it is. And I'm going to end up keeping you like 3 or 4 minutes late. I hope that's all right. So R2, R3, R4. I don't have an R1 there. Don't worry about why. So let's call this I2, I3, I4. Okay. So now let's look at this. What are we feeding back? A current. Yes, we're feeding back a current. We're taking something from the output, feeding back a current, we're shunting it here. Now there's something very important worth noticing. What if instead of this, I had done this? What are we feeding back now? A voltage or a current? We're still feeding back a current. Even though the input source is a voltage, like this is a Norton equivalent, Thevenin equivalent to a voltage, to a current source with just a shunting resistor, right? And so what you have to realize is that sometimes the input and output terminals, or the input and output stimuli, are not a direct indication of what you're feeding back. You can sort of see how, so I'll just put this here again. You can sort of see how you're feeding back a current here. Well, does anyone not see how you're feeding back a current? Does that make sense to everyone? Yeah? Okay, this is relatively obvious. Okay, so that means at the input it's a shunt network, right? So what are we sensing? Who thinks current? One person. Who thinks voltage? One person. Who thinks charge? We're actually sensing a current. Because even though this is where it's tricky. Even though the output is V out, what you can see is whatever current flows to make V out, I4, comes directly out, and that's what's being manipulated and sent back. Okay? We're basically sensing I4. So that's series. We're sensing a current, and that's series. So in order to redraw this, so that we can calculate what the feedback factors and forward loop gain and all that other stuff is, and then we'll call it a day. So M1 and M2. Oops. Okay, so again, our main amp is here. And actually R4 is out here. And our feedback network is there. Okay, so in order to figure out the feedback, remember it's shunt over here, series over there. Okay, so I out is coming out through here. How much of it gets fed back? So what we have, our feedback network looks like this. I out, R3, R2. This is I feedback. And because it's a shunt on this side, this looks like a low impedance node. Okay? From there, we can directly calculate that F, it's just a current divider, is equal to R3 over R2 plus R3. Okay? And we can do a similar sort of experiment, or a similar sort of exercise with A to calculate what the forward loop gain is. Okay? And the thing is that this then it gets into, in order to formally calculate what A is, you need to keep in mind that this resistor network loads both the input and the output. But I don't think Professor Broderson has got to that yet, so I don't want to get ahead of him in lecture. Okay? So basically, you can calculate the feedback network. You can calculate the forward loop gain, and then from there, calculate how the gain is, what the overall gain is. And because this is a series feedback, the gain will be unitless. It'll be current in, current out, and then multiplied by R4 to get the voltage out. Okay? So that's it. Any questions? All right. Have a good weekend. I almost ended on time this time.
I know those answers are correct.
Okay, if this person worked between 75 to 100 hours, he's gonna make at least $50.
Yeah.
Then you added,
Overtime is only for the hours you do
So he's-
over 50 hours.
so, okay, he doesn't get overtime, so he's gonna get approximately 25 hours when
No. Okay, so he's gonna get at least 50 hours.
and no bonus, right? Okay.
No bonus. No overtime. He's gonna work between 75 and 100 hours. The halfway point for that is 8 7. Or 8. Yeah, 8 7 84.
Oh yeah, that's right. No common sense here.
That's not what I got.
Sorry.
The variance is like ridiculous.
I don't know. It's supposed to be the square as you go along. So you put in 100 overtime. So
I'm making it short.
okay, you get average of that is 50, 100. You get person looking at least 75 hours, 25 plus average of that is 4.5, 4.5, 25.25, 37.5, 75. Fuck, yes. Don't change my what?
That's what I got too. It doesn't make sense. No, no, no.
100, 1,100.
Can someone explain that to me? Does that mean half the time he doesn't get paid or something? I think you're right.
So, look here, if I can look through it here.
God! I erased the wrong fucking phone.
Okay, I'm gonna be guys all of it.
Okay, I think someone's fucking working
I wish he gets paid in 1 week.
No, that's a good point.
Not a lot. This man gets paid $1 an hour. That is really ridiculous wages.
So he's gonna work. Okay, he gets all of this. He's gonna work 50 plus overtime, so he'll get plus
You're not supposed to work over 64 hours a week.
well, the way he gets paid, he has to. Plus overtime, so
On average, this man only gets paid $68 a week, you know?
I almost do that, but
People get paid that in an hourly rate.
25 plus 100.
We call it profession. Well, we're the same number.
86.
You find the expected value of the expected value of t squared given thing, and then you subtract that minus the square root of, the square of the, yeah, the moment formula.
Got some kind of 48 for the.
That'll be like minus 8 off.
Which motivation? God, you're gonna kill me here. I get no overtime, so this person's unfortunately gonna get 50 plus whatever he was about 50. So you're doing 75, so that's 25, which was 25.
For what time?
29.
No,
I didn't use convolution at all.
you make them go up the sides. Not using convolution. Yeah. You just take out e to the s, take out e to the
You take it, you do the s, and then it becomes a formula.
b, you just gotta take the e to the 3s out and you have like the geometric random variable. Yeah, and then you just, it's just shit.
I look it out, but I didn't know how to translate from anything.
Wait, it's negative, right? Wait, what's that one? What? Yeah, okay. Yeah, right. So 8 equals 28, 160.3. because I use the same variance of variance formula. I know the expected value, I know the variance, I know the mean and the variance of both sides. And so I can just plug and plug and I get 164 again. Yep. You see, that's the mean. We know the variance. We know the mean. We know 20, we know 16. Okay, we get 20 and 16 for the mean. Right, 16. Did you get it?
Your mean is wrong. Your mean is supposed to be 8 squared before.
I can't even add nowadays.
Probably aspect of turning the class.
How did I get 20 for something squared?
You give yours to someone else.
Oh,
Thank you for
I can't
making
remember nowadays.
I'll give mine.
What I give it to?
Just give me Frank. Okay, just turn it in. Okay.
No, variance, that's not the variance, that is the variance.
Not now, but like
Yeah,
later on.
yeah.
Cool, thank you.
That is the variance, remember, so it's not the variance squared. That's the standard deviation. That would just be the variance, which is 20. Then I have 64. So just make fucking answer. Come on! So much sheep. 4 times 20 divided by, no, I got it. Okay, hold on, relax. 400, well, I can do that. 400 divided by 3 plus 64 times 20.
If you get the variance of n,
I know the variance is n. I know it's a binomial or something like that.
the variance of binomial is 119.
I got actually, no, it's not binomial. This is n p times n 1 minus p. So what I say? What's the Kafka?
Yeah, that's fine.
Yeah, 276. Yeah, but that's my
Take the square root of that.
What?
Take the square root of that. Go. Take the square root of that number.
16.63.
That should be fine, right?
Oh, yeah, 30 being.
No, because the mean is 8.
What's L? L is the
No, hold on. The expected value is 160. 160 divided by 3. Yeah, so that's 53. So it's about. It's okay.
Yeah.
Go for it.
I need it. So, for this one, it's just a trial.
Yeah.
Or it's not.
Yeah. Pretty much it. Which one are you looking at?
Okay. Well, B is just a geometric sign, or geometric plus or.
Yeah, that's just, yeah, exactly. Yeah.
Okay.
So you just put the formula in there.
No, no.
Oh, the sum?
Yeah, it's just the 10 choose k, 3 plus k, and 1 third, the 10 minus k.
This is for the variance.
Yeah, that's pretty good. Got it? But I need 22 back again. Let's come up with the expected value and take the hit. I don't want to take the hit. Fucking meters. Dude, like lose one thing, you lose 5 points, it's like gone.
I hope that happens to like a little bit.
I doubt it.
It's less than what?
It's either 3 S.
sheet from there with lots of color marks on it and put it in. What?
Yeah, because now I have it, but what am I gonna
Hmm? Zero? I couldn't get my final answer.
That one was really small. It was like something
Sure, of course. I'm very close, but I don't have a final answer. Because we are kind of
No, you just take a little bit of that comes zero. So then you just simplify. Oh, sorry, my bad.